Microsoft Excel can be a powerful tool to assist with data preparation. In this presentation, you will be offered examples of data prep and data visualization using Microsoft Excel. We will begin by covering procedures for editing, recoding, and creating new data with Microsoft Excel. One thing to note about using Microsoft Excel is that data can be imported in a variety of formats. First, you can export data from a database and work with that data in Microsoft Excel. Typically, these datasets are formatted as comma-separated values files, otherwise known as a CSV file. There are some peculiarities working with the CSV file in Excel that we will cover. Data in Excel cannot exceed 1 million rows. If there is more than 1 million rows, the file will be truncated. A CSV file is a text file, which can actually be previewed using Notepad. A CSV file contains one row of data on each line, and each field is separated by a comma. The first line typically contains the header, otherwise known as the column names. If you open a CSV file in Microsoft Excel, the software will read the commas and know exactly how to separate the data into respective columns and rows. You can see this from this example. You need to be cautious when you work with a CSV file in Microsoft Excel, particularly when you are saving the data. First, if you have numerous worksheets with data in them and you save the Excel file as a CSV, only the active worksheet will be saved. The active worksheet is the worksheet that is open at the time you save. Second, all formulas will be removed once you save the file as a CSV. This is only the case after you close the file down and reopen it in Microsoft Excel. If there are leading zeros, such as the case with zip code, they will be removed when saving as a CSV file. Therefore, if you plan to edit the data, use formulas, have multiple worksheets, and need leading zeros, the best approach is to save the data as an Excel file, otherwise known as an XLSX file. To open a CSV file in Microsoft Excel, you should follow the following steps. First, open Microsoft Excel. Next, go to the Data tab. Then click on the From Text button listed in the General External Data section. You will select your CSV file on the Navigator window that appears. Follow the text import wizard and make certain that you select the comma as the delimiter. Now the data should open in Microsoft Excel. Now you can save the file as an Excel workbook by going to File, Save As, choose your desired location, and from the drop-down next to Save As type, choose Excel Workbook. Let's begin by examining methods of recoding data in Microsoft Excel. Consider when you need to recode data. Some instances may be when you need a series of numbers to a category or to convert text to a number. For instance, we may want to recode a column that includes sex, and instead of the variables being male and female, the data is formatted as a 1 and 2. Another example may be where we convert numbers to a category, such as converting a column of ages into age groups. You may also need to consolidate categorical data into smaller groups, such as the case if you want to combine states and represent the data as regions. Regardless of the type of recoding, it's important to consider a few things. First, consider how you will handle blank entries, null or zero values. You may or may not want to include them in your analysis. When recoding, ensure that you have complete coverage of the data to avoid introducing missing data or null values. For instance, if you wanted to recode length of stay so that anything less than 5 days is given the text low, and anything greater than 5 days the text of high, what happens if the length of stay is equal to 5 days? This should be accounted for appropriately using the logical operators. Maybe you should say anything less than or equal to 5 days should be given low, and all other values the text high. Logical operators are a staple of recoding data. They allow us to test the truth of conditions. When a statement is found to hold true, we often carry out an event, versus when it is false, we carry out a different event. Boolean operators or logical operators are used to generate rules and test the truth of a statement. These are commonly formatted as greater than, less than, greater than or equal to, less than or equal to, or not equal to. The way to format these as a logical operator may be as shown. If you want to test if A is greater than B, we use the function A, the greater than sign, and B. If this is true, then A would in fact be larger. If it is false, then B is greater than or equal to A. You can see the other logical operators stated on this table. These are the most commonly adopted methods that are used in Microsoft Excel. The question is, how do we use these logical operators to determine if the statement is true or false? The answer is to adopt the if statement. For instance, if we had two cells of data in Microsoft Excel, cell A1 and cell A2, and those cells contained numeric data. If we wanted to test if the data in cell A1 is greater than A2, we would use the conditional statement A1, the greater than sign, A2. If that statement is found to be true, we can return an output. For instance, in this example, we can return the output higher. If that statement is false, we return lower. The if function is one of the most popular functions in Excel and allows you to make logical comparisons between a value and what you expect. In its simplest form, the if function says, if something is true, then do something, otherwise do something else. Therefore, an if statement can have two results. The first result is if your comparison is true, the second is if your comparison is false. For example, if we wanted to test whether a number in cell A1 is greater than 3, we can use the logical test A1 greater than 3. When that statement is true, we can return the text high, and when this statement is false, we can return the text low. You can also use conditional statements for text. For instance, we can test if the data in cell B1 is equal to the character A. If this is true, we can return a 1, and when this is false, return a 0. Here's an example as shown in Microsoft Excel. Let's look at the top example. Listed under the column name named Active is the text Yes, which is found in cell C2. In cell D2, we type in our if function. We start this function with an equal sign and then type the if and an open parentheses. Next, we specify our conditional statement. In this example, we want to test if the data in cell C2 is equal to yes. If this is true, we will return a 1, and if this is false, we will return a 2. After you hit enter, you will see that the number 1 is returned because our conditional statement was found to be true. One note is that when using a conditional statement in testing if certain text appears, we will always place quotation marks around the text. This is also true if you want text to be returned. The example in the middle of the screen shows something a bit different. Instead of the text yes listed in cell C2, now we have a 1 listed. Let's change our conditional statement to test if the data in cell C2 is equal to 1. If this is true, we want the word yes returned, and when false, the word no returned. Note that we have quotes around the yes and no due to the fact that this is text. The final example is testing a conditional statement using data found in two different cells. As shown, There is data that has the budgeted expenses in column B and the actual expenses in column C. If we wanted to test the statement regarding whether our actual expenses exceed our budget, and when this is true, to return text indicating if we are over or within budget, we can use the if function. In cell D2, we type in the formula equals if in open parentheses and enter our conditional statement to test if the data in cell 2 is greater than the data in cell B2. If this is true, we return the text over budget. If this is false, we return the text within budget. Go through these examples on your own in Microsoft Excel and try to manipulate the data to see what happens if the statement is found to be false. Oftentimes, we want more than just two outputs returned with a conditional statement. In these cases, we can use what is called a nested if function to test more than one conditional statement and return more than two outputs. This is the practice of joining multiple functions together in one formula. For instance, what if we wanted to have three categories where we test if data found in cell A1 is less than or equal to 0.33 and then is recoded as low? A value from 0.33 to 0.66 is middle, and a value greater than 0.66 is high. An if function can be used, but in this case, we have to use a nested if function. That is, embed a second if function in place of the true or false value to offer the option to redirect the output to more than just two outputs. Think of this as a decision tree. With a single if function, we would have two lines diverging from the tree, one for true and one for false. Therefore, if A1 is less than or equal to 0.33, we return the text low. If we embed another if function in place of the false output, we can now create two outputs in place of the false. Therefore, if A1 is greater than 0.33, we then test another if function. We test if A1 is greater than 0.66. If the second if function is true, we return the text high, and if it is false, we return the text middle. Why would we return text middle if the second statement is false? The reason is because from our first if function, we know that the data is greater than 0.33, but less than or equal to 0.66. Therefore, it falls within our middle range. The way to write this as an if function in Microsoft Excel is shown below the diagram. It's an equals if, open parentheses, A1, a less than sign, then an equal sign, 0.33, then a comma, then in quotation you put the text low, and then a comma, and then in place of false you have another if function. If, open parentheses, A1 is greater than 0.6, then a comma. If that is true, return the text high, and then a comma, and if that is false, return the text middle. Here's a more complicated example. Assume we wanted to convert a number grade to a letter grade. We can use a nested if function to test many conditional statements. Follow along with this example to ensure you understand how the nested if function is working. We can test if the data found in cell D2 is greater than 89. If this is true, we return the letter grade A. If this is false, then test if the score in cell D2 is greater than 79. If that is true, then return a B. If that is false, then test if the score is greater than 69. If that is true, return a C. And if that is false, test if the score is greater than a 59. If that is true, return a D. And if that is false, return an F. You can see how this can start to get a bit complicated with numerous nested if functions. In fact, you can add up to 64 nested if functions. Although you can do this, you probably shouldn't. Why is that? Well, by having so many if functions, it opens the chances of an error because there is so much to keep track of. It's important to understand the difference between the use of the AND operator and the OR operator. They do entirely different things. The AND operator should only be used if you want to include criteria that occur together. For example, if you wanted to test how often sex is equal to male and age is greater than 18 to return the text adult male, since there are two conditions that must be satisfied and co-occur to return the text and operator, and the AND operator is used. The OR operator is used only if you want to include criteria where either can occur separately. For example, if you wanted to recode several states, then when the text WI for Wisconsin, IL for Illinois, MI for Michigan, or MN for Minnesota occur, the text Midwest will be returned. Since only one of the following states needs to be present in order to return Midwest, the OR operator is the most appropriate. Here's an example of how to use the AND operator in Microsoft Excel. Assume we want to test if the value in cell A2 is less than the value in cell A3, and also determine if the data in cell A2 is less than 100. If both of these criteria are true, we return the data in cell A2. If false, we return the text, the value is out of range. You'll note that when we write the formula with more than one criteria in the if function, that the AND occurs prior to stating each criteria. Each criteria are then separated within parentheses after the AND function. The OR function works similarly, but tests the criteria differently. For instance, if we wanted to test if the data in cell A2 is greater than 1, or the data in cell A2 is less than 100, when this is true, we return the data in cell A3, otherwise return the value is out of range. Again, you'll see that the OR function occurs followed by a parenthesis and each criteria is specified and separated by a comma. As stated, the data extracted from a database is typically saved as a CSV, but can be opened and manipulated in Microsoft Excel. It can also be saved as a .xlsx file. The if function is incredibly powerful for recoding data. It can save a lot of time when data prep when used appropriately. Next, we will discuss data transformation, removing, and validation using Microsoft Excel. With data preparation, it is recommended to create summaries of the data to determine the need for data transformation, removal, or validation. For instance, if we discovered that the average length of stay for inpatients was 22 days, which seems high, we may want to know how many inpatient visits there were, if there were outliers, or anything skewing the data, thereby causing a misrepresentation of the mean. Therefore, we will cover out how to carry some simple data summaries in Microsoft Excel, including average, median, min, max, and standard deviation. One important step with data prep is testing the distribution of the data. Histograms are incredibly difficult to create in Microsoft Excel, even though this is the best way to know the distribution. There is a shortcut, however, that we will cover. To summarize, a histogram tells you about how often a quantitative value occurs. The numeric value is broken down into groups along the x-axis to establish the width of the bars. The height of the bars represents the frequency of how often each binned quantitative value occurs. There are numerous types of distributions. The normal distribution is shown in the upper left-hand side of the screen. You'll see it follows a nice bell-shaped curve. The distribution in the upper right is called a negative or left skewed distribution. If you were to look at the average would be skewed to the left due to the influence of the low values. However, the median would be close to the hump of that distribution. A positive skew occurs when the data is skewed to the right. This causes the mean to be slightly higher than the median. A bimodal distribution occurs when there are two humps in the distribution. This often occurs when there are categorical differences in qualitative values. For instance, if data for males and females were plotted together for some lab data, this could cause a bimodal distribution. A shortcut in Microsoft Excel to test the distribution is to calculate the average and the median. If the average is significantly greater than the median, the data is positively skewed. If the average is quite a bit lower than the median, the data is negatively skewed. Unfortunately, this shortcut cannot test for bimodal distribution. Now this video will demonstrate how to calculate the mean, median, and mode in Microsoft Excel.
Anybody remembering their school days will remember that for average, there are actually 3 different commands. Those 3 commands can all be achieved in Excel by use of 3 different functions, obviously. The 3 commands, as we know them in mathematical terms, are mode, median, and mean. The mode is the most frequently occurring value within a given range. So for our range here, if we are looking at bananas sold throughout the year, the most frequently occurring value in that range would be the mode. The median is the middlemost value within a range. So you would take away the highest and the lowest values until you are left with the middle value. That's the median. The mean, which is the most commonly known one that we work on as an average, is effectively the total of all the values divided by however many there are. So in our case here, there are 12 values. It will total all of those up and divide by 12. Now the mean function in Excel is referred to as average. So it's equals average, open brackets, highlight the range, return. And we get a value of 30.333333 recurring. So 30 and a third. Now we can control the decimal places by changing the number format to number, and we get 2 decimal places. Now the way that Excel works with its average or mean function is to add up the total of numbers and divide by however many there are. Now if we remove a value from the range, we'll find that there is a new total, but it's now only dividing by 11 because there are 11 cells with numbers in. It doesn't just divide by the number of cells in your range, but by the number of cells with numbers in. So it's quite vital that there is that difference. So that's the average function. Now the mode function is equals mode. Highlight your range, return, and we find that 45 is the most occurring value in the range. In fact, it occurs twice. And then median, the middle value is median, equals median, open brackets, highlight the range, return, and it gives us a median of 23. Now all 3 of those can actually be referred to as the average, but they are worked out and calculated in different ways. All 3 of those methods achievable in Excel using the average function, the median function, and the mode. We can then take all 3 of those and replicate them across all of our different fruit. And we find it returns obviously different values. Everything is relative. Now there is one little caveat with the mode. If there is no mode, if there is no recurring number, so we have 9 there as the mode because it happens 1, 2, 3, 4 times. Let's change that so that one of the other numbers meets it. Now 4 is the mode. Add a 6 in. 4 remains the mode, even though it occurs twice and 9 occurs twice. So there's a little item to be careful of there. If, however, there are no unique values, so if, for example, I took that 4 down to be a 1 and that 9 to be 76, then we get returned an NA, because there is not one mode in that range, because all 12 values within the range are unique. If you find that you have repeating modes, then it will use the lowest value. If there are no modes and not one value has effectively more than one occurrence of itself, then you'll get the NA return for not applicable. This does not happen with the median or the mean. The median is always the middle value regardless of however many values there are, and the mean is always the total divided by however many values there are.
Why is it important to test the distribution? First, it helps to identify outliers that may affect the data. Therefore, it helps to determine if average is an appropriate way to summarize the middle value. If the data is skewed, the average may be misleading. Ultimately, if the data is skewed, we may need to transform, remove, or validate the data. There are several types of data transformations that can be performed. The two we will discuss is a square root transformation and a log transformation. The square root transformation consists of taking the square root of each observation. In Excel, this is given by the sqrt function. It is commonly used when the variable is a count of something. The back transformation is to square the number. If you have negative numbers, you can't take the square root. You should add a constant to each number to make them all positive. The log transformation consists of taking the base 10 log of each observation. In Excel, this is given by the log function. The back transformation then is to raise 10 to the power of the number. In Excel, you use 10, and then the caret and y, where y is the number you wish to back transform. If you have zeros, you can't take the log. You should add a constant to each number to make them non-zero. If you have count data and some of the counts are 0, the convention is to add 0.5 to each number. The video here will illustrate how to do data transformation in Excel and the impacts that it has on the data.
Hey everyone, so today we'll do an introduction to transforming data, and just before we start I wanted to kind of give a refresh. I've briefly mentioned in a couple of these lessons this idea of just a best fit line, and we haven't, if you've been following straight through with these lessons, we haven't formally defined what a best fit line is, but I just want to remind you that the way we think of a best fit line is if I've got a bunch of data, so in this case the data is just these blue dots here. Okay, so it's actually more of a curve, and it's sort of a perfect curve, but this is a very theoretical example. But the idea is that if I wanted to linearize that data, if I wanted to look at it in terms of a linear relationship, so as time goes up, I have some slope of the line, and the population of this place called Faketown increases in a linear way, I can just take a line and draw it right through that data. Okay, and this line is the best fit line, and Excel can do this for you, and most of the statistical packages can do this for you pretty easily. And it'll actually give you an equation also. So here's the equation of this line. It says that y is equal to 31.235x minus 59,258. The negative number here is not really very meaningful, but actually the slope is the important thing here. This says that each year the Faketown is gaining approximately 31.235 people. And this r squared, which again we also will go into starting next chapter, this kind of gives you tells you how good the relationship is. It varies between 0 and 1, and if you're closer to 1, it tells you that the relationship there is a good correlation between these two variables, time in years and the population of Faketown. Okay, so I just wanted to remind you of that concept. Now that we've kind of talked about x versus y, we're going to talk about when we want to actually manipulate these variables. So up until now, we've looked at things very simply in terms of this, time versus population, right, in a very, very simple sort of way. Well, what if we wanted to manipulate this data to make it a little bit neater? What if we wanted to make it actually fit on this line? Or what if we were looking at, say, CEO pay, and we wanted to make this data symmetrical because, geez, CEO pay is really not symmetrical, as you can see from this graph. So if I wanted to do something like that, I could do something called transforming the data. And specifically today, we're going to talk about log transformations. They're the most common type of transformation that's done. In fact, most researchers, the only transformation they'll ever use will be just log transformations. So we'll get that out of the way. And we'll continue later on and talk about more transformations, but for now that should be sufficient just as an introduction. So here's an example of a highly skewed distribution, and here's CEO pay in the Fortune 500 companies, 500 large companies in the United States. Okay, so we've got the CEOs in the Fortune 500, so there's obviously 500 total CEOs here, and we've got their total comp in thousands of dollars. So 1,000 here actually means $1 million. So as you can see, the comp is really skewed, right? It's really skewed to the right, as we say, because there seems to be a peak right around $1 million, maybe a little bit over $1 million, and then this really steep slope and a bunch of data that, well, I can't really tell if they're outliers because I don't really know where the center of this data is. Is it here? Is it here? Right? Is it the mean? Is it the median? It's very tough to tell. So I've got a problem here, right? I want symmetrical data, but I just don't have it. And if I was comparing this distribution year over year or something, it would be very difficult for me to tell if CEO salaries had gone up because, well, there's no real left tail of the distribution. Again, don't really know where the center is. Should I be using the mean or the median? It's a bit questionable. So let's talk about one way we can manipulate this data, transform this data to make it a little bit cleaner and a little bit nicer, so we can kind of examine it in a more logical way and compare distributions and all those things we like to do with box plots and things like that. Okay, so here we go. Here's the transformed distribution, and what I did was I took the logarithm of CEO pay. So just to remind you of what a log is an exponent. So for instance, if I was looking at CEO pay of $1 million and I just took the log of $1 million, recall that a million is just 10 to the 6th, right? It's a 1 with 6 zeros after it. Okay, so if I took the log of 10 to the 6th, the log of $1 million, I get a value of 6. Okay, so this tells me that instead of classifying this CEO's salary as $1 million, I'm going to actually just classify it as 6. And what this does is it brings everybody closer together in the distribution. So as you can see, there's a lot of guys with 6-figure CEO salaries. This is actually up to 6 figures. I think these are the guys who are actually between 5 figures and 6 figures. So this is 100,000. So this would be a log of 5 up to a log of like 5.99999, that sort of thing. So this is 100,000 to 1 million. And I've more appropriately lumped those guys together. Okay, so the distribution, as we can see, really, it doesn't make sense to really separate the guys who are $1 million to $9 million because they're really all the center of this distribution, right? I should really include kind of all these guys as the center of the distribution, and then I can really determine who are the outliers here. Okay, so I've got the 100,000 guys to $1 million guys. I can see that the 7-figure salary guys, so the 1 million guys up to 9,999,999.99 these guys seem to be the peak of the distribution. So I can now say that $1 million up to $10 million is really my the peak of my distribution. It's really the center of my distribution. So what I've done is I've kind of scrunched up the data, and now I can say, hey, a CEO making $10, which I couldn't really see over here, whether that CEO even existed, just due to my scale. A CEO making $10 is unusual, right? He's an outlier in this data. Whereas a CEO making $100,000 is really not unusual, and you might say that a CEO making between 10 and 100,000 is not that unusual either. He's just very low on the curve. On the other side of things are guys who are making 10 to the 9th dollars. So these are guys making $1 billion and over. So we could say actually that these guys are not that unusual on the log scale, right? They actually look like they're part of the distribution. So this has allowed me to kind of better examine my data, and now I've got a much neater sort of box plot. If I were to plot this data, it would look nice and neat, just like I like it to. Okay. Now, one thing your book notes, which is a funny thing, is that if you are an outlier on a log scale, you are seriously an outlier. So a guy making 10 to the 10th, so $10 billion plus, not sure who really does that, maybe Bill Gates in some years or somebody like that, or Warren Buffett. If you are this guy, you are indeed quite an outlier in this data. So the log just makes this data nice and neat for us. Where else can we use logs? Well, we can use logs when growth isn't linear. This is actually a really common place where you use logs. So population growth, for instance, is usually a percentage growth concept. So this population, I think I set it to be growing at about 1.5% per year. Well, if something's growing at 1.5% per year, that's not a linear concept, right? If I start with 1,000 people in the population, then the next year I'll have 15 more people, but the year following that I'm going to have more than 15 more people, right? Because it's 1.5% of 1,015, not 1.5% of just 1,000 anymore. So this is not a linear gain. It's not like I'm going to gain 31 people each year. That doesn't make any sense. I'm actually going to gain more than that in some years and less than that in other years. And as you can see, the line kind of misses most years here. It's not quite right, except for in a couple of places. So what we can do is we can actually take the log of the population. So if we take the log of the population, this will actually linearize the data. And so what you're seeing here is you'll note the equation changed. The r squared also changed. It's a perfect r squared now because the population is actually growing a percentage change. And if you take the log of a percentage change, I won't go through the math here, but if you take the log there, it will actually perfectly linearize the data. And now we're looking at the log of the population of Faketown versus the year, and I can now draw a best fit line through that, like we were talking about before, and I actually get a perfect best fit line. So taking the log of the data was actually a really useful thing to do here. So you might ask, well, okay, that's great. I've got the log of the population. What the heck does the log of the population mean? Well, the answer is it doesn't mean a whole lot. The log of the population is just the log of the population. You'd have to do 10 raised to the log, if you remember your log rules, 10 raised to the log of the population to get any kind of meaningful population out of this. This would give you the actual population in a given year. But what you do get out of this equation actually is that this slope here is actually log of 1 plus the growth rate. So in other words, if I call it log of g and say that's equal to this 0.0065 that I got up here, I can actually find my growth rate really easily, because it turns out that if I find g here, so 10 raised to the 0.0065, then I find that that's 1.015, and that 0.015 is my 1.5%. That's my growth rate. Okay, so if I take the log of the population, the equation that I get for the best fit line here will actually tell me what my growth rate is. I just do 10 raised to the slope, and that'll tell me my 1 plus my percentage. And that'll give me my growth rate. So that's kind of the useful thing that you can take out of this, as well as getting a really nice best fit line for which you can find population at any given point just by using this equation, 10 raised to the log of the population. Okay, so that's just an introduction, and we're going to do more transformations later, but I wanted you guys to see that you can indeed not just take x and y variables, but you can actually look at the log of y, and that's often an interesting thing to do. So we transform data for a number of reasons. One is problems of scale, symmetry or spread issues. So here in particular we had a big symmetry issue, highly skewed distribution. When the distribution is skewed to the right, you will use a log scale, and the log scale will give you a nice symmetrical distribution, or a more symmetrical distribution. So symmetry or spread is one thing. And the second thing that we talked about was just linearizing data. So if we suspect there's a nonlinear relationship, so if it's percentage growth in particular, so if you're looking at biological applications where cells are growing by some percent growth rate, for instance, you're looking at a tumor growth rate or something, the slope is not constant. We want to linearize that data, so we'll actually take the log of the number of cells instead of just the number of cells, or in this case we'll take the log of the population of people. Instead of just the population versus time, we'll actually look at the log of the population and compare that to time. So that's another reason, and then we can draw a best fit line through that very often, and we can find our constant percent growth rate as we talked about. And there are other common transformations. So another common transformation that people do is taking square roots. They also do inverse transformations where you actually take the data, instead of having just y as the data, you might do 1 over y, so you can get the inverse as well. And a lot of these just depend on, what fits the data best. Is the data right skewed or left skewed? In this case, the most common thing that you see is really right skewed data. So we just talked about log transformations, where you're typically going to use you'll typically use those in right skewed data. But these other ones also exist, and you may see them as well, and they do different things to the data and can be helpful when you don't have symmetry and when you don't have linear data. Okay, thanks a lot.
Understand that by transforming data, you are changing the face value of a number. This may confuse your audience, so make note if a data transformation is used. Only transform data if it is absolutely necessary. For instance, some inferential statistics require data to be normally distributed to work properly. Therefore, a transformation may be necessary. You may also want to do a transformation to ensure that calculating means is the best way to represent the middle value. To avoid data transformations, use data summaries that make sense. These include using median versus the mean, looking at count or frequency, and looking at the minimum and maximum. This video will demonstrate how to use the sum, count, minimum, and maximum functions in Microsoft Excel.
Let's start with the basic functions so that we can make sure that we are happy and all heading in the same direction. We're going to take the sales data 2013 file, and in here there are 12 months worth of data, January through to December. And all we want to add in is the mathematical formula that will sum the sales for each region, that will count the number of sales for each region, produce the lowest sales value for each region, and the highest sales value for each region. 4 simple functions. Just to add in a slight bit of complication, we're going to select all of the sheets by clicking on Jan and then shift clicking on Dec for December, and you'll see that all 12 sheets are selected. This will give us the advantage that when we add these formulas into these cells here, it will replicate through all 12 sheets, saving us quite a lot of work. Adding up, hopefully we are aware it's equals sum, open brackets, highlight the cells we wish to add up, and then return, tab, whatever your preference is, to finish the equation. So that's summing B3 to H3. So we take our formula, and instead of dragging down to replicate as normal or copy and paste, what we're going to do is go to the little fill handle, grab hold with the right mouse button instead of the left, and you'll notice the cursor has changed shape, drag down to the bottom, that is as normal, let go, but now we choose to fill without formatting. And what that does is it then copies the formula down, but retains the cell's original formatting, so we have the right dotty blues and black border on the right, instead of having the black border top and bottom. So that's the sum function. Count, just as straightforward, equals count, open brackets, select our range of items to count, return, lowest sales equals min. So these are all straightforward mathematical functions. Return, and the same for the highest sales equals max. Highlight the correct cells, return. So this time we'll take all 3 mathematical functions, grab the fill handle in the bottom right hand corner, but with the right mouse button, all the way to the bottom, let go, fill without formatting. And we find that our count is the same. Our lowest cells picks up the lowest value in the particular range, and the max brings up the highest value in that particular range. Now, because we linked all 12 sheets together, those same formulas will be replicated throughout all 12 sheets. Now we can have a look at them while they're still grouped, and you can see there is a slight difference between the figures in each of them. And you'll also notice that if you click 3 or more times, the group becomes deselected as a group, and we are now dealing with these as separate sheets, not as 12 sheets grouped together. So that's just something to be a little bit aware of if you are grouping sheets and then looking through them, that sometimes the group will ungroup if you click around too often. So that's the 4 basic functions that you're likely to use to any degree of frequency. Sum for adding up, count for counting the number of cells with numerical content, min for the smallest value in a given range, and max for the highest value in a given range.
Data replacement may be necessary in some instances. Often, a data replacement occurs because of the presence of filler data. For instance, you may need to remove text that states data wasn't available. Alternatively, if there are filler values, you may need to replace them. You may also want to replace extreme outliers with a blank entry. The question is oftentimes whether you should remove the entire row of data or just that value when you find an erroneous value or missing data. It's really up to you. If you are carrying out an analysis and comparing different rows of data, for example, length of stay and cost of encounter, it may be best to remove the entire row. However, if you're simply summarizing a single column of data, it should be okay to just remove a single value. If there is a need to just replace the value itself, you can use the Find and Replace function in Microsoft Excel. On the Home tab in the Editing group, click Find and select. Now enter in the data you want to find and enter in the data you want to replace, and then click OK. You can use wildcard characters, such as an asterisk or a question mark. In your search criteria, use the asterisk to find any string or character. For example, S*D finds sad and started. Use a question mark to find any single character. For example, a S*T finds sat and set. Here's an example of the Find and Replace in Microsoft Excel.
In this tutorial, we're going to show you how to search, find, and replace content in Excel. In Excel, you can locate cells by using the Find and Replace command. Suppose you wanted to locate a cell or cells that contained a certain word or number. Instead of searching throughout your workbook, you could use the Find and Replace command and let Excel do the work for you. First, we'll cover how to find content. In the Home tab, under the Editing group, click on the Find and Select command, and from the drop-down menu, click on Find, and the Find and Replace dialog box will appear. The Find and Replace dialog box has two tabs, the Find tab and the Replace tab. Where it says Find What, enter the content that you want to locate. Now click on the Options button and more search options will appear in the dialog box. Here you have options of Within, Search, Look In, Match Case, and Match Entire Cell Contents. Use the options to tailor your search and press Find All. The Within option. Here you can choose to search a single worksheet or the entire workbook. The Search option. Here you can organize your search by rows or columns. If you were to choose by rows, then your search results would be organized by rows. The very next cell in the search would be the very next cell in the row that contained your data. If you organize your search by columns, then the very next cell in your results would be the next cell in the column that contained your data. The Look In option. Here you can choose to search inside formulas, comments, and regular values for your data you want to locate. The Match Case option. If this box is checked, then your search will be case sensitive. Match Entire Cell Contents. If this box is checked, then the cell or cells found must contain only the search string and nothing else. How to replace content. Imagine you had a large inventory list with the names of multiple suppliers. What if one of the suppliers changed their name? It would be very time consuming to change the company name cell by cell. Instead, you can use the Find and Replace command and change all cells instantly. In the Find and Replace dialog box, make sure that the Replace tab is activated. The only difference with the Find tab and the Replace tab is that you have a new box and buttons that allow you to replace the cells in your search results with other content. The options work the same in Replace as they do in Find. Make sure that you use the Match Case and Match Entire Cell Contents if necessary. If you searched and replaced the number 3 with 5 without checking the Match Entire Cell Contents option, then the number 2 would be replaced with the number 5 even if it was in a series of numbers. For example, the number 638 would be 658 after you click Replace All or Replace Next.
In Excel, you can use filtering to present data that meets specific criteria to find extraneous values. To work with the data effectively and use filters effectively, storing the data as a table can help. Let's take a look at an example. To store the data as a table, first select the range of cells you want included in the table. The cells can't be empty, and it must contain data. Then go to the Insert tab and click Table. If the top row of the selected range contains data you want to use as the headers, then select the My Table Has Headers checkbox. Then click OK. To filter the data, click the arrow in the table header of the column you want to filter. In the list of text or numbers, you can uncheck the Select All box at the top of the list, and then check all the boxes of the items you want to show in the table. Then click OK. You can remove a filter by clicking the Clear Filter option as shown. In conclusion, data transformation, replacement, removal, and filtering are important steps in preparing data for analysis.